There are 40 billion Earth-sized planets sitting in the habitable zones of stars in our galaxy alone. 40 billion places where liquid water could pool on a surface, where temperatures permit the chemistry of carbon and hydrogen and oxygen to do what it does on Earth, where the conditions for biology are not just possible, but probable. The observable universe contains at least 2 trillion galaxies. If you multiplied 40 billion by 2 trillion, if you tried to count every potentially habitable world in the observable universe, you would reach a number so large that it loses meaning entirely. A number that dwarfs the total count of every grain of sand on every beach and ocean floor on Earth by many orders of magnitude. We have been listening for signals from any of these places for 65 years, with telescopes sensitive enough to detect the equivalent of a single large television transmitter from stars hundreds of light years away. With algorithms now processing data 600 times faster than 5 years ago, with instruments covering every frequency band in which a technological civilization might plausibly transmit, with searches covering not just individual stars, but entire galaxies, 2,800 of them surveyed in a single program, each containing hundreds of billions of stars. The result is a number. That number is 0. Not approximately 0, not nearly 0 with some marginal candidates still under investigation. 0. Every candidate signal in 6 decades of searching has resolved, eventually, into noise or interference or a natural phenomenon that nobody predicted beforehand. Every signal that initially looked promising turned out to be a pulsar, or local electronics, or background galaxies, or statistical artifacts in the data reduction pipeline. 12 billion candidate signals processed by volunteer computers over 21 years. 0 confirmed. 74 million narrowband hits recorded from the direction of an object that arrived in our solar system from interstellar space. 0 artificial. The number has not changed since Frank Drake pointed an 85-foot dish at 2 nearby stars in 1960 and heard nothing. This is the starting point for everything that follows tonight, not a mystery waiting to be solved by better instruments or more patience. A measurement, a hard, accumulated, statistically constrained measurement that has been converging on the same answer for 6 decades across dozens of independent programs using different telescopes at different frequencies in different parts of the sky. The universe is silent. And the silence is the most terrifying data point in the history of science. Not because it proves we are alone, it does not, but because of what it implies about what happens to civilizations that reach the point we are at right now. Civilizations that build radio telescopes and ask questions about the universe and send signals into the dark. The silence is not an absence of information, it is information. Specific, quantifiable, deeply uncomfortable information about the fate of intelligence in a universe that appears to have had every opportunity to fill itself with it, and has not. Tonight, we are going to follow that information honestly, from the mathematics of why silence is so improbable given what we know about planets and chemistry and the origin of life, through the specific mechanisms that researchers now believe are filtering civilizations out of the observable universe, to the 2 papers published in the last 2 years that placed the most likely filter not behind us in the distant past, but directly ahead of us in the near future. If you are here because the night is long and you need something to think about, stay. This is one of those subjects where following the evidence carefully produces something that cannot be unfelt. A specific kind of vertigo that comes from understanding not just that the universe is silent, but why it probably is, and why that why is directly relevant to what happens next on this planet. Let us start with the mathematics of the problem, with the specific calculation that makes the silence not just puzzling, but, in a precise statistical sense, catastrophically strange. The Milky Way galaxy is approximately 13.6 billion years old. It contains somewhere between 200 billion and 400 billion stars. We now know from the Kepler Space Telescope's survey of roughly 150,000 stars that virtually every star has at least one planet. The fraction of stars with planets, which astronomers called FP in the Drake equation and originally guessed might be around 0.2, turned out to be closer to 1.0. Every star. The revision upward by a factor of 5 happened in a single decade of observation. Further analysis of Kepler data estimated roughly 40 billion Earth-sized planets in the habitable zones of their stars in our galaxy alone, places where liquid water can exist on a surface, where the temperature range permits the organic chemistry that produces biology on Earth. And the origin of life appears to be fast. This is the finding that makes the silence most strange. Earth formed approximately 4.54 billion years ago. The last universal common ancestor of all life on Earth, the single organism from which every living thing on this planet descends, existed approximately 4.2 billion years ago. The gap between the formation of the planet and the confirmed presence of life is somewhere between 300 and 400 million years, and much of that window was spent under conditions actively hostile to biology. The surface was partially molten. Asteroid bombardment was intense. The chemistry of early Earth was violent and unstable. Life did not wait for favorable conditions. It appeared essentially as soon as liquid water became stable on the surface. In geological terms, this is not a long process. If you compress the entire 4.54 billion year history of Earth into a single calendar year, life appears before the end of February. This matters enormously for what the silence implies. If abiogenesis, the transition from chemistry to biology, is fast and robust and tolerant of difficult conditions, then it is almost certainly happening on many of those 40 billion habitable worlds right now, and has been happening for billions of years before now. The galaxy should be biologically active on a massive scale. And yet, 65 years of listening at every frequency, with instruments sensitive enough to detect deliberate transmissions from hundreds of light years away, has produced nothing, not a confirmed signal, not an anomaly that survived serious scrutiny. Not a single narrowband hit that could not eventually be traced to a natural source or human-generated interference. The gap between what the math predicts and what we observe is not small. Statistical models built on 6 decades of null results now constrain the number of detectable technological civilizations in the Milky Way to fewer than 1 to 5 per century. Not per year, per century. Across a galaxy containing hundreds of billions of stars, each almost certainly hosting planets, on a world where life appears within geological instants of favorable conditions forming, the number of expected civilizations and the number of observed civilizations differ by a factor so large that it demands an explanation. Something is filtering them out. Not something vague or metaphorical, something specific. A bottleneck, or a series of bottlenecks so severe that the vast majority of the chains of development leading from simple chemistry toward detectable technology are being broken somewhere before they complete. The question is not whether a filter exists, the silence proves it does. The question, the one with implications that are either deeply reassuring or deeply terrifying depending on where the filter turns out to sit, is when in the chain the breaking happens. In 1996, an economist named Robin Hanson formalized this problem in a paper that reframed it more precisely than anything that came before. Between dead chemistry and a civilization sending signals across interstellar distances, there is a long sequence of steps: forming a planet, developing organic chemistry, crossing the threshold from chemistry to biology, developing complex multicellular life from single-celled organisms, evolving nervous systems and cognition, building technology, surviving long enough to become detectable. If the galaxy should be full of detectable civilizations, but is not, at least one of those steps must have a pass rate so close to zero that almost nothing gets through. Hansen called this the Great Filter. The concept is purely probabilistic. You do not need to know which step is the bottleneck. You only need to accept that the silence requires one to exist. And the question that makes the Great Filter the most unsettling concept in science, more unsettling than any individual catastrophe or disaster, is whether we have already passed it. If the filter sits behind us, in the early steps in the transition from chemistry to life, or from single-celled to complex multicellular organisms, then the hard part is already over. We passed through something extraordinarily improbable and emerged on the other side. The silence makes sense because almost nothing else ever made it this far. We are rare, but we are safe. The worst is behind us. If the filter sits ahead of us, in the later steps, in something that happens to civilizations that reach approximately our current level of development, then the silence is a graveyard. Every civilization that got this far, that built the equivalent of radio telescopes and particle accelerators and global communication networks, eventually hits a wall it does not survive. The silence is not the rarity of intelligence. It is the systematic destruction of intelligence at a specific threshold. Under this scenario, we are at the threshold right now. For decades, the optimistic interpretation seemed more defensible. The emergence of complex multicellular life does appear to be genuinely difficult. Earth spent roughly 2 billion years as a world of single-celled organisms before the jump to multicellular complexity. Intelligence took another 2 billion years after that. These long timescales suggested the early biological transitions might carry much of the filtering weight. We passed them. We are on the lucky side. Then 2 papers appeared within 2 years of each other in 2024 and 2026 that shifted the weight sharply in the other direction. Both papers proposed filters ahead of us. Both described mechanisms already underway and already measurable in current data. Neither required speculation about exotic physics or unknown catastrophes. Both required only an honest extrapolation of trends already visible on Earth right now. Let us talk about the first one. In 2024, an astrophysicist named Michael Garrett published a paper proposing that artificial intelligence is the Great Filter. The argument was built on a specific observation about timelines. Humanity sent its first radio transmissions in the 1890s. Roughly 127 years later, generative artificial intelligence systems began operating at levels that surprised even the researchers who built them. The transition from first radio signal to sophisticated artificial intelligence took approximately 1 century. Garrett's model treats this trajectory as universal, not because every civilization will make identical technological choices, but because the underlying pressures that drive the development are the same wherever intelligence emerges. Economic competition rewards efficiency. Military competition rewards capability. The logic of tool improvement is directional. Once you develop electronics, the development of increasingly autonomous computational systems follows from the same pressures operating in the same direction. His estimate for the window between a civilization developing artificial intelligence and being fundamentally altered or destroyed by it is approximately 200 years. Not thousands, not millions. 2 centuries. 2 centuries is the total duration during which a civilization might be broadcasting detectable electromagnetic signals while still existing in a form that produces those signals. Now apply that window to the mathematics of detection. The Milky Way is 13.6 billion years old. A civilization's detectable phase lasts 200 years. That is a ratio of 1 to 68 million. The probability that any 2 civilizations exist within detection range of each other and are simultaneously in their 200-year window of leaky electromagnetic emission, simultaneously, not separated by thousands of years, is vanishingly small, even if civilizations are relatively common. Garrett's model does not require artificial intelligence to physically destroy a civilization, though that is one possibility. It also accounts for transformation. a species that merges with its machines or is replaced by post-biological intelligence that has no interest in radio communication, no need to broadcast, no motivation to announce its existence. The observable signature disappears regardless of the mechanism. The window closes. The civilization goes dark. Consider Earth's own trajectory as evidence. In the mid-20th century, Earth was electromagnetically loud. Analog television broadcasts, omnidirectional radio, military radar systems operating at enormous power. These signals leaked into space in every direction and were, in principle, detectable by any sufficiently sensitive instrument within a few hundred light-years. We are already getting quieter. Fiber optic cables carry data through glass rather than through the air. Streaming services replaced broadcast television. Digital compression makes signals look like random noise to any receiver that does not have the decryption key. Military radar is transitioning to phased arrays that focus energy in tight beams rather than radiating omnidirectionally. The unintentional electromagnetic footprint of Earth has been shrinking for decades and will continue shrinking. Within 50 years, Earth may be effectively undetectable to any instrument outside the solar system, not because we were destroyed, but because we became more efficient. Technology itself made us invisible. If this is universal, if every civilization that develops electronics follows the same trajectory from loud to quiet as it becomes more technologically advanced, then the silence is partly explained by physics and economics, rather than catastrophe. Advanced civilizations do not broadcast. Efficiency selects against leakage. But Garrett's model gives civilizations only 200 years. Even accounting for civilizations that become quiet rather than extinct, the window is extraordinarily narrow. And then there is the second paper. In 2026, a researcher named Darren Dugan proposed a mechanism that does not require machines at all. No technological singularity, no existential catastrophe, nothing external, nothing sudden. Just mathematics applied to a trend already visible in the demographic data of every industrialized nation on Earth. Dugan's filter is the decoupling of reproduction from survival. In every species that exists below a certain threshold of intelligence and technology, reproduction is functionally automatic. Individual organisms do not consciously choose whether to reproduce. The pressures of evolutionary fitness ensure that those inclined to reproduce do, and those not inclined do not pass that disinclination to descendants. Reproduction is driven by biology, not by deliberate decision. As intelligence increases, as cognition becomes sufficiently complex to model the future, to understand causality, to weigh costs and benefits across long time horizons, something changes. Reproduction becomes a choice, a considered, deliberate choice, made against the background of a full understanding of what that choice costs. In a subsistence environment, children are labour, additional hands that increase the group's ability to gather food and defend territory. In a technological environment, children are expensive. They require years of resource investment, time, money, attention, during which they produce nothing economically and consume heavily. The calculus inverts. And when that calculus inverts, and when individuals have effective control over whether they reproduce, fertility rates fall. This is not a projection or a model, it is an observation. The fertility data from industrialized nations is unambiguous. South Korea's total fertility rate in 2024 was 0.72. For every 2 adults in South Korea, fewer than 1 child. Replacement requires 2.1. South Korea is producing children at approximately 1/3 the rate needed to maintain its population. Japan is at 1.2, Italy at 1.24. China dropped below replacement in 2022, and the rate continues falling. Every wealthy industrialized democracy on Earth has fallen below replacement, and most are significantly below it. Pro-natalist policies, government programs specifically designed to reverse these trends through financial incentives, parental leave, subsidized childcare, have been tried by multiple governments and have uniformly failed to produce sustained reversal. France, which has the most generous family support system in Europe, still fell below replacement. Hungary spent years implementing aggressive pro-natalist policies and produced only marginal, temporary increases before the downward trend resumed. Dugin's model treats this as thermodynamic rather than political. Not a problem to be solved with the right policy mix, but an emergent property of intelligence itself. Specifically, of intelligence sophisticated enough to model the future consequences of reproduction with enough fidelity to make the costs feel immediate and the benefits feel abstract. His projections map current trends forward. Human population peaks around 2080 at roughly 10 billion, then enters a decline that accelerates with each generation, because a population with below replacement fertility produces a smaller cohort of potential parents in every successive generation, which produces a still smaller cohort after that, compounding downward. By 2500 in his model, the global human population is below 100 million. By 3000, functional extinction. Not from war or asteroid impact or climate catastrophe, from a quiet, irreversible demographic mathematics playing out across generations. And if this is universal, if every species intelligent enough to control its own fertility follows the same curve once industrialization removes the economic incentive to reproduce, then the silence has a second explanation that does not require any external catastrophe at all. Civilizations arise, they develop technology, they decouple reproduction from survival, they dissolve across centuries, leaving no ruins dramatic enough to detect from light years away. Just empty maternity wards and aging populations, and eventually, silence. The two filters, Garrett's artificial intelligence window of 200 years and Duggan's demographic decline over 500 to 1,000 years, are not mutually exclusive. A civilization might face both simultaneously, and the trends driving them are already measurable in human data right now. We are 127 years into the electromagnetic window that Garrett's model gives us. The demographic trends that Dugin's model requires are already underway in every industrialized nation. We are not discussing hypothetical future risks. We are describing current trajectories already in motion. This is what makes the silence terrifying, in a specific and personal way. Not because something unknown is coming for us from outside, but because the data about what is coming can be read in birth rate statistics and in the progression of artificial intelligence systems, and in the quiet shrinking of our electromagnetic footprint as technology advances. The silence is not evidence that we will definitely die. It is evidence that civilizations like ours, civilizations that have reached approximately our current level of development, almost universally go quiet within a time frame measured in centuries rather than millennia or millions of years. And we are already well into that time frame. Let us now talk about what this implies for the specific structure of the universe we observe, about why the silence is consistent with not just one or two of these mechanisms, but with all of them operating simultaneously, each one narrowing the window independently. The Drake equation has 7 variables. Astronomers have now measured 4 of them with reasonable precision. The rate of star formation in the Milky Way, approximately 1 to 3 stars per year. The fraction of stars with planets, essentially 1.0. The fraction of those planets in habitable zones, roughly 1 in 5 for Sun-like stars, more for red dwarfs. The speed at which life appears given favourable conditions, very fast, within hundreds of millions of years of surface cooling. Every measured variable has moved in the optimistic direction. Every revision has increased the expected number of civilizations. The variables that remain unmeasured, the fraction of life-bearing worlds that develop intelligence, the fraction of intelligent species that build detectable technology, the average lifespan of detectable civilizations, must therefore carry the full weight of the filtering. Because the product of all 7 variables must equal a very small number, a number consistent with 0 detections across 65 years of increasingly sensitive searching. Stern and Gerrier's 2024 paper estimated that the fraction of life-bearing planets developing intelligence is between 0.003 and 0.2%. If correct, this alone reduces the expected number of civilizations dramatically. But even at 0.2%, the optimistic end of their range, 40 billion habitable worlds produces 80 million worlds with intelligent life across the Milky Way's history. That is still an enormous number. Spread across 13.6 billion years of cosmic time, the probability that some of them overlap with us in time and space and are detectable should be non-zero. So the intelligence bottleneck alone does not fully explain the silence. Then add the lifespan variable. If detectable civilizations exist for 200 years, Garrett's window, the calculation changes dramatically. 80 million civilizations spread across 13.6 billion years, each existing for 200 years. At any given moment, including right now, the expected number of simultaneously existing detectable civilizations in the Milky Way is approximately 1, including us. The math does not require the filter to be a single catastrophic event. It requires the product of all the filters to be small enough that civilizations are either extremely rare or extremely brief, or both. And the evidence increasingly suggests both are true simultaneously. Intelligence is genuinely rare, and civilizations that develop it are genuinely brief. The silence is the product of this compounding. Not one impossible thing, but many improbable things multiplying together to produce a universe that looks empty from where we stand, even if it is not technically empty. Let us talk about what has happened to the instruments we built to break that silence, because the history of the search itself contains something important about how seriously our civilization has treated this question. The Big Ear radio telescope at Ohio State University operated from 1963 until 1998. It was this instrument that recorded the WOW signal in 1977, a 72-second burst of narrowband emission at exactly the hydrogen line frequency that remains the strongest candidate for an artificial extraterrestrial signal in the entire history of the search. It passed every test available at the time. It behaved exactly as a deep sky artificial transmission should behave. Decades of subsequent analysis have moved the scientific community away from an extraterrestrial explanation. The current best hypothesis is a rare, natural phenomenon called a hydrogen maser flare, triggered by a magnetar, a type of coherent emission from interstellar gas that nobody had predicted beforehand. But the signal was never definitively explained, and the telescope that found it was demolished in 1997 and 1998, when the land was sold to a developer who built a golf course. The most compelling candidate signal in 65 years of searching. The telescope that found it, a golf course. The Arecibo Observatory in Puerto Rico operated from 1963 until 2020. For 53 years, it was the most sensitive single-dish radio telescope on Earth. It was used for SETI, for asteroid radar mapping, for pulsar research, for atmospheric studies, and for dozens of other scientific programs. In August 2020, one of the cables supporting its receiver platform snapped, then another. Engineers warned that the structure was at risk of catastrophic collapse. The National Science Foundation decided that repairing it was too dangerous and announced it would be decommissioned. On December 1, 2020, the receiver platform fell. 900 tons of equipment crashed through the 305-meter dish beneath it and destroyed both. The NSF chose not to rebuild. The Allen Telescope Array in California, 42 dishes built specifically for the search for extraterrestrial intelligence were shut down in 2011 because the SETI Institute could not afford $1.5 million a year to keep it running. A single F-35 fighter aircraft costs $80 million. The array was later reactivated with private funding, but the shutdown illustrated a pattern that has defined the entire history of the search. The federal government funded dedicated SETI research for exactly 1 year. NASA launched the High-Resolution Microwave Survey in 1992 with a $12 million annual budget. Senator Richard Bryan of Nevada defunded it in 1993. $12 million, approximately the cost of 600 feet of interstate highway. The amount required to maintain one of the most scientifically significant programs in history was less than the rounding error in most federal budgets. Since 1993, the search for extraterrestrial intelligence has been funded almost entirely by private donors. The question of whether we are alone in the universe, a question with implications extending to every field of human thought, including philosophy, religion, ethics, and long-term civilizational planning, depends on the charitable giving of individual billionaires. This is itself a data point, not about the universe, about us, about what our civilization considers worth resourcing at a serious level. In 2015, Yuri Milner announced Breakthrough Listen, $100 million over 10 years, the largest private investment in SETI history. It scanned approximately 1 million nearby stars. It accumulated more than 2 petabytes of data. It used the most sensitive radio telescopes on Earth, including Green Bank in West Virginia, Parkes in Australia, and Meerkat in South Africa. It found nothing. And the Parkes telescope, part of the Breakthrough Listen network, did find something in 2020 that for a period seemed like it might be the result everyone had been waiting for. A narrowband signal at 982.002 MHz, appearing in data collected while the dish was pointed at Proxima Centauri, the nearest star system to our own. A system already known to host at least one planet in the habitable zone. The signal was designated BLC-1, Breakthrough Listen Candidate 1, the first candidate the program had ever considered promising enough to earn a formal designation. It drifted in frequency in a way consistent with a transmitter on a rotating planet. It appeared when the dish was pointed at Proxima and disappeared when the dish was pointed away. It survived months of internal analysis. It survived multiple rounds of filter application. Researchers checked it against databases of satellites, aircraft, ground-based transmitters. It kept surviving. Then, in 2021, the team found structurally similar signals at nearby frequencies that had nothing to do with Proxima Centauri. The frequency drift that had seemed diagnostic was found to be producible by local interference under certain conditions. The on-off behavior could be explained by secondary sensitivity lobes in the telescope's own beam geometry, picking up local signals at specific pointing angles. BLC-1 was radio frequency interference from electronics operating within the telescope compound itself, approximately 0 light-years from Earth, the most exciting SETI candidate in decades, generated by human equipment a few hundred feet from the receiver. This pattern, a candidate signal appearing, surviving initial scrutiny, generating genuine scientific excitement, and then collapsing into a mundane explanation nobody had anticipated, has repeated throughout the entire history of the search. Pulsars in 1967 looked like regular artificial transmissions, until they were understood as rotating neutron stars. The WOW signal looked like an artificial transmission until the magnetar-triggered maser hypothesis. The Dyson sphere candidates in 2024 looked like megastructures until background galaxy contamination was identified. BLC-1 looked like Proxima until the telescope's own electronics were identified as the source. The universe keeps generating false positives that fool increasingly sophisticated instruments, and the true positive, if one exists, has not yet appeared. Let us now talk about something that the silence implies about the specific position we occupy, about what it means to be a civilization at our current level of development. given what the data suggests about what happens to civilizations at our current level of development. We have been broadcasting electromagnetically for approximately 100 years. The sphere of our unintentional electromagnetic emissions currently extends roughly 100 light-years in every direction, encompassing approximately 15,000 stars. Any civilization with a radio telescope comparable to Green Bank located within that sphere and pointed at the right frequency during the right century could detect us. We are already getting quieter as described. The unintentional leakage from Earth has been declining for decades and will continue declining as technology advances. Garrett's model says civilizations have approximately 200 years between first radio and the artificial intelligence transition that either ends or fundamentally transforms them. We are 127 years in. Duggan's model says civilizations that survive the artificial intelligence transition face demographic decline beginning within the first few generations of industrial prosperity, a decline that accelerates with each generation and becomes effectively irreversible once the population age structure has sufficiently inverted. Every major industrial economy on Earth is currently in this decline. The trends are not projected, they are measured. These two filters do not require any external threat, no asteroid, no alien civilization, no single catastrophic event, just the internal dynamics of what happens when intelligence reaches a certain threshold of capability, and when prosperity decouples reproduction from survival. And the silence suggests these dynamics are not unique to Earth. They appear to be features of intelligence itself, rather than features of any particular civilization's choices. Every civilization that reaches approximately our point appears to go quiet within centuries, not because of bad luck, because of what intelligence does when it becomes sufficiently powerful. This is what makes the silence terrifying in a way that is different from and more personal than any individual existential risk. It is not that some specific disaster is coming, it is that the trajectory of intelligence appears to contain within itself the mechanisms of its own quieting. That the same cognitive capacity that allowed us to ask, "Where is everybody?" to build radio telescopes and write equations and search the sky, also produces the conditions that explain why the sky is silent. We are asking the question from inside the answer. There is one more dimension of the silence worth examining tonight. Not what it implies about other civilizations, but what it implies about what we would do if the silence broke. In 1999, a Russian astronomer named Alexander Zaitsev used the Evpatoria planetary radar facility in Crimea to transmit a high-powered, targeted message towards several nearby star systems. He called it Cosmic Call. He did not seek international consensus. He did not consult the broader scientific community. He did not need to, because there is no binding international protocol governing deliberate transmissions from Earth into space. There are voluntary guidelines from the International Academy of Astronautics. Anyone with access to a sufficiently powerful transmitter can announce humanity's existence and location to the galaxy right now, today. No treaty prohibits it, no law governs it. The decision about what Earth says to the cosmos, if anything, rests with whoever happens to control the equipment at any given moment. The reaction from the scientific community was immediate and deeply divided. Some argued that deliberate transmission was reckless, that if the dark forest hypothesis had even marginal probability of being correct, announcing our location was the equivalent of making noise in a forest full of armed hunters. Others argued that Earth's military radar had already been leaking our location for 70 years, and hiding was pointless. Both arguments were made seriously by serious people, and neither has been resolved. The dark forest hypothesis, proposed by Chinese science fiction writer Liu Qi-chin in 2008 as a solution to the Fermi paradox, holds that the silence is not the absence of civilizations, but the collective behavior of civilizations that have learned silence is the only safe strategy. In a universe where resources are finite and every civilization knows that every other civilization is a potential threat, the rational strategy is to remain undetectable and to eliminate any detected civilization before it can become a danger. Every civilization that survived long enough to still exist has independently arrived at this conclusion. Every civilization that made noise was eliminated. The galaxy is not empty. It is a dark forest full of hunters standing motionless. The hypothesis cannot be proven or disproven, but it is consistent with the observations, and it implies something specific about what we have been doing for 100 years of unintentional electromagnetic leakage. We have been making noise in the forest. Whether anyone is listening, whether the forest contains hunters, or whether it is truly empty, is precisely what 65 years of searching has failed to determine. What we know is the number at the end of every pipeline. The number produced by 12 billion processed candidates, by 1 million surveyed stars, by 74 million narrowband hits from an interstellar visitor, by 28 hours of continuous observation of a 7-planet system, by the largest Dyson sphere search ever conducted. The number is 0. And 0 is not nothing. 0 is a measurement about the universe that has something specific to tell us about where we are and how long civilizations at our stage tend to persist, and what the trajectory of intelligence looks like when followed honestly to its conclusion. The instruments keep getting more sensitive. The searches keep getting larger. FAST, the 500-meter dish in Guizhou province in China, the largest single-aperture radio telescope ever built, is currently reobserving 100 candidate signals that survived 21 years of distributed computing from SETI at home. The James Webb Space Telescope is searching for biosignatures in the atmospheres of exoplanets. Machine learning is accelerating data processing by factors of hundreds. The window is still open. The question Enrico Fermi asked at a lunch table in Los Alamos in 1950 has not been answered. But the data has been accumulating for 65 years, and it is starting to say something that was not audible in the early decades of the search. Something systematic is happening to civilizations between the moment they first become detectable and the moment they would need to persist for us to find them. The silence is not waiting for a better telescope. The silence is a measurement. And the measurement is about us. Let us talk about something that sits at the precise intersection of what we know and what we fear, about the specific mathematical relationship between the age of the universe and the window of detectability, and why that relationship produces a conclusion that most people are not psychologically prepared to absorb. The Milky Way has been forming stars for approximately 13.6 billion years. The earliest generations of stars were metal poor. They lacked the heavier elements like carbon, oxygen, nitrogen, and silicon that complex chemistry requires. Each generation of stars that lived and died seeded the interstellar medium with heavier elements, forged in stellar cores. By approximately 8 to 9 billion years ago, stellar populations rich enough in heavy elements to support rocky planets and organic chemistry were becoming common. This means complex chemistry, the kind that leads to biology, has been possible in our galaxy for approximately 8 to 9 billion years. We have existed as a technological civilization for 100 years. The ratio is 80 to 90 million to 1. If technological civilizations arise with any regularity across that 8 to 9 billion year window, and if they persist for any significant fraction of that window, the galaxy should contain overlapping signals from thousands or millions of them simultaneously. The sky should be full of noise from civilizations at various stages of development, some young, some ancient, some expanding, some contracting. Instead, the sky is silent. The only way to reconcile a universe this old with a galaxy this quiet is if civilizations are either extraordinarily rare, so rare that the entire 8 to 9 billion year history of complex chemistry in the Milky Way has produced only a handful, or extraordinarily brief. So brief that even if many arise, they do not persist long enough to overlap with each other in time, or both. Garrett's model of a 200-year detection window represents the most extreme version of the brevity argument. But even if you are generous, even if you extend the window to 1,000 years, the math does not change dramatically. 1,000 years against 8 billion is a ratio of 1 to 8 million. For two civilizations to be simultaneously detectable by each other, they need to arise within the same 1,000-year window, within detection range of each other, pointing instruments in the right direction at the right frequency. The probability is not zero, but it is small enough to explain the silence without requiring any additional mechanism. What this means concretely, the most likely explanation for why we have not heard from anyone is not that nobody exists. It is that the windows during which civilizations broadcast and the windows during which they persist are so narrow relative to the age of the galaxy that even a universe full of civilizations produces silence to any individual observer within it. We are a brief flash in an old, dark room. The other flashes, if they exist, are separated from us by millions of years of cosmic time. We are not contemporaries, we are sequential. One arising after another falls dark, with millions of years of silence between. This is a specific and testable implication. If the brevity argument is correct, we should expect to find dead civilizations, archaeological evidence of technological activity from civilizations that existed millions of years ago and are now extinct, long before we find any living ones. The ruins should vastly outnumber the active settlements. We have not found the ruins either, but the absence of ruins is less surprising than the absence of signals. Ruins require us to visit the systems where they exist, or to develop imaging technologies sensitive enough to detect planetary scale modification from light years away. We have neither capability. Signals we could receive without leaving the solar system, and we have been trying to receive them for 65 years. The silence on signals is the primary constraint. The absence of ruins adds to it, but does not independently establish it. Let us now talk about something that most discussions of the Fermi paradox skip, about the specific asymmetry between what it takes to send a detectable signal and what it takes to receive one, and why this asymmetry changes the statistical picture in ways that matter. Receiving is easy. A 100-meter radio telescope, the kind that exists at several locations on Earth, is sensitive enough to detect a signal equivalent to a large television transmitter from several hundred light years away. If any civilization within a few hundred light years is deliberately broadcasting in our direction at moderate power levels, we would probably detect it. Sending a detectable signal is harder. The signals Earth produces unintentionally, the electromagnetic leakage from radar and broadcasting, are detectable only from a few hundred light years away with instruments comparable to our own. Across most of the galaxy, Earth is invisible. The overwhelming majority of the Milky Way, everything beyond a few hundred light years, would require deliberate, high-power, directional transmission from Earth for us to be detectable from there. This asymmetry matters because it means the 65 years of silence does not tell us that civilizations within a few hundred light years do not exist. It tells us that no civilization within a few hundred light years is deliberately sending signals in our direction at detectable power levels right now. They might exist and simply not be broadcasting. They might be broadcasting but not toward us. They might be broadcasting in frequency ranges or encoding schemes we have not searched. They might be broadcasting using technologies we have not conceived, tight beam laser communication, for instance, or modulation of stellar output, or quantum entanglement channels, if such a thing is eventually proven possible. The silence constrains the number of civilizations deliberately broadcasting omnidirectionally at radio frequencies within a few hundred light years of Earth. That is a much narrower constraint than it first appears, and yet, even accounting for this asymmetry, even acknowledging that our search has covered only a tiny fraction of possible communication modalities, the null result after 65 years of the most sensitive search ever conducted for the specific signals we know how to detect is significant. Not because it proves silence, but because it rules out a specific scenario that would have been extremely likely if the galaxy contained many advanced civilizations with the motivation and technology to be heard. If any civilization within a few thousand light years had achieved something like a Kardashev Type 2 energy level, capturing a significant fraction of its star's output, and had decided to broadcast, we would almost certainly have detected it by now. The power levels involved dwarf anything we have searched for. A Dyson sphere civilization transmitting even a tiny fraction of its available power toward Earth would produce a signal drowning out everything else. The fact that no such signal exists places a hard upper bound on the number of Kardashev Type 2 or higher civilizations within a few thousand light years that are actively trying to communicate. That number is 0, or very close to it. Поговорим теперь о конкретном явлении, делающем молчание еще более странным. О том, что мы знаем о времени жизни звезд, и о том, что это говорит нам о том, сколько времени было у жизни, чтобы развиться до технологического уровня в разных частях галактики. Наше Солнце – звезда среднего возраста. Ему около 4,6 миллиарда лет, и у него еще приблизительно 5 миллиардов лет до того, как оно начнет расширяться и уничтожит внутренние планеты. Красные карлики, наиболее распространенный тип звезд в галактике, живут триллионы лет. Некоторые звезды в нашей галактике существуют с момента почти самого начала. Им 12 или 13 миллиардов лет. Рядом звезд, которые на 2-3 миллиарда лет старше нашего Солнца. Если жизнь появилась вокруг них с той же скоростью, что появилась вокруг нас, в первые несколько сотен миллионов лет пригодных условий, у нее было на 2-3 миллиарда лет больше для эволюции. Представьте, что означает от 2 до 3 миллиардов лет дополнительного эволюционного времени. Первые многоклеточные организмы появились на Земле около 600 миллионов лет назад. Первые животные с нервными системами около 5000 миллионов лет назад. Первые наземные позвоночные около 365 миллионов лет назад. Весь промежуток от первых животных до нас около 5000 миллионов лет. Цивилизация на планете на 2 миллиарда лет старше нашей имела бы дополнительное время, равное 4 таким промежуткам. 4 полных эволюционных цикла от первых животных до технологической цивилизации. Что бы такая цивилизация построила за 2 миллиарда дополнительных лет технологического развития? Мы перешли от первого радиосигнала до искусственного интеллекта за 127 лет. Экстраполировать, что происходит за 2 миллиарда лет технологического прогресса за пределами этого, значит говорить о чем-то так далеко превосходящем наши нынешние возможности, что нет ни одного мысленного эксперимента, способного это содержать. И таких систем, звездных систем значительно старше нашей с планетами в обитаемых зонах, должны быть сотни миллионов в нашей галактике одной. Где они? Не просто где их сигналы, где следы того, что они сделали.
Потому что цивилизация с 2 миллиардами лет технологического развития должна была бы иметь ресурсы и время для изменения своей звездной системы, своего соседства, возможно, значительной части галактики, способами, обнаруживаемыми без специального оборудования. Мы видим галактику, которая выглядит нетронутой. Звезды ведут себя так, как предсказывает физика. Планеты формируются и разрушаются по астрофизическим процессам. Межзвездный газ движется предсказуемо. Нет структур, явно созданных интеллектом. Нет паттернов, требующих разума для объяснения. Это немалое наблюдение. Это одно из наиболее сильных ограничений на существование древних технологических цивилизаций в нашей части галактики. Либо такие цивилизации не существуют, либо они существуют, но намеренно скрыли каждый след своего существования с точностью, которую мы не можем обнаружить. Либо они существуют, но не расширялись, не строили ничего большего, чем их родная система, не оставили никаких мегаструктур, не произвели никакого детектируемого изменения окружающей среды. Каждая из этих альтернатив требует объяснения. Первое, что они не существуют, означает, что возникновение разума является настолько редким, что за от 8 до 9 миллиардов лет химии, способной к биологии в нашей галактике, мы можем быть буквально первыми или среди первых немногих. Вторая, что они скрыты, требует предположить, что каждая цивилизация независимо пришла к решению стать необнаружимой и выполнила это с идеальной эффективностью. Ни одна утечка, ни одна звезда, ведущая себя необычно, ни одна случайная деградация мегаструктуры, видимая через световые годы. Полное подавление обнаруживаемой активности на протяжении миллиардов лет. Третье, что они существуют, но никогда не расширялись, требует объяснения, почему ни одна из многих цивилизаций за миллиарды лет не решила расширить свое существование за пределы родной системы, что систематически делает межзвездную экспансию непривлекательной или невозможной для каждой цивилизации, которая когда-либо существовала. Ни одна из этих альтернатив не является комфортной. Все они требуют либо исключительной редкости, либо исключительного поведения, либо исключительного ограничения. Let us now talk about something that most popular treatments of the Fermi paradox give insufficient weight, about the specific implication of the silence for our own civilizational planning, and why the answer to "where is everybody" is directly relevant to decisions being made right now. If the great filter is behind us, if the emergence of intelligence is the rare event, and we are one of the few or the only, then our long-term responsibility is different from what most people assume. We are not one civilization among many. We may be the only repository of the accumulated information of biological and cognitive evolution in a significant portion of the observable universe. The stakes of our survival are not just civilizational, but cosmic. If we fail, nothing inherits what we have learned. The experiment does not get another attempt in this corner of the galaxy. If the great filter is ahead of us, if artificial intelligence or demographic decline or some other mechanism systematically terminates civilizations at approximately our level of development, then the relevant question is whether we can identify the mechanism clearly enough to navigate around it. The pattern that produces the silence is not necessarily fatal. It is only fatal if it runs unrecognized and unaddressed. Garrett's model that artificial intelligence represents a 200-year window between detectability and either destruction or transformation does not require artificial intelligence to be inherently dangerous. It requires that the transition happens faster than civilizations can adapt governance frameworks to manage it. The danger is not intelligence itself, but the speed mismatch between technological development and institutional capacity to direct it. Duggan's model, that demographic decline follows from the decoupling of reproduction from survival, does not require civilization to collapse. It requires the trend to run without countervailing pressure. Whether that countervailing pressure is possible, whether the demographic mathematics is truly as irreversible as his model suggests, is an open empirical question. Some researchers argue that cultural shifts, value changes, or sufficiently restructured economies could reverse fertility decline at scales that government pro-natalist policies have not achieved. The evidence so far does not support optimism, but the evidence so far represents only the early decades of the trend. In both cases, knowing about the filter changes the probability of surviving it. A civilization that does not know about the demographic cliff does not see it coming. A civilization that has precisely mapped its demographic trajectory has at least the option of responding to it deliberately. This is one of the specific ways in which taking the Fermi paradox seriously is not an academic exercise. The silence is not merely an astronomical mystery, it is a constraint on what happens to civilizations like ours, derived from 65 years of observation of the most relevant sample we have, the universe itself. The universe has run the experiment of intelligence many times over.
The result, as far as we can tell, is always the same. The intelligence arises. It becomes detectable. It goes quiet, usually within centuries. We are in the detectable phase right now. We are 127 years into it. The question is whether understanding this changes anything about what happens next. Let us talk about what the most recent searches have found, not as a summary of past efforts, but as a description of what the current frontier of the search looks like and what the null results from that frontier imply. The cosmic instrument on the Very Large Array in New Mexico began operating in March of 2023. It is a commensal system. It piggybacks on all other observations the VLA performs, processing the same data in parallel without competing for dedicated telescope time. In its first 11 months of operation, it observed more than 950,000 unique fields, covering 267,510 individual stars across the frequency range of 2 to 4 gigahertz, including the water hole, the quiet band between the hydrogen line and the hydroxyl line that has been considered the most logical channel for intentional interstellar communication since the 1970s. The result from 950,000 fields? 0 technosignatures. The Meerkat Array in South Africa, 64 dishes designed for the next generation of radio astronomy, surveyed 2,800 entire galaxies for signs of technological activity. Not stars, galaxies, each containing hundreds of billions of stars. The logic was that a sufficiently advanced civilization producing energy at galactic or near-galactic scale might be detectable across intergalactic distances. The Meerkat result: nothing. The Allen Telescope Array observed TRAPPIST-1, a red dwarf 39 light-years away, hosting 7 rocky planets, 3 in the habitable zone, for 28 continuous hours during planetary occultations, when any transmitter on one of those planets would be in the most favorable geometric configuration for detection. The observation produced 2,264 candidate signals. Every single one was traced to terrestrial origin. Then, in July of 2025, an object arrived in our solar system from interstellar space. Designated 3I/Atlas, it was the third confirmed interstellar visitor, following Oumuamua in 2017 and Borisov in 2019. The Allen Telescope Array pointed at it within days. Over 7.25 hours of observation, it recorded 74 million narrowband hits. Automated filters reduced that to 211 candidates worth closer examination. The final count of unexplained signals? 0. 74 million signals from the direction of an object that traveled to us from another star system. Not one was artificial. These numbers, 950,000 fields, 2,800 galaxies, 28 hours on 7 rocky planets, 74 million hits from an interstellar visitor, represent the most thorough search for extraterrestrial signals ever conducted. The instruments involved are more sensitive than anything available even 10 years ago. The data processing is faster, the frequency coverage is broader, the analysis pipelines are more sophisticated. The number at the end of all of them is the same number that has emerged from every search since 1960, 0. At some point, the accumulation of null results across independent programs using independent instruments in independent parts of the sky becomes something more than a gap in knowledge waiting to be filled. At some point, 0 is a finding. That point has been reached. Statistical models built on the accumulated null results constrain the number of detectable technological civilizations in the Milky Way to fewer than 1 to 5 per century, not per year, per century. Across a galaxy of 200 to 400 billion stars, each almost certainly hosting planets, with life that starts fast wherever conditions permit. The hot tub argument, the defense that we have only searched a tiny fraction of the cosmic ocean and cannot conclude anything from not finding fish in one scoopful, has been eroding under the volume of the accumulated search. It was a valid argument in 1960. It became less valid after SETI at home processed 12 billion candidates. It became less valid after Breakthrough Listen surveyed 1 million stars. It became less valid after Cosmic covered 950,000 fields commensal with the VLA. It is less valid today than it was yesterday. 0 is converging to a measurement, and the measurement is saying something about the universe that we have not yet fully absorbed. Let us now talk about something that connects the silence to a specific and rarely examined philosophical question about what it would mean to confirm that the filter is behind us versus ahead of us, and how these two confirmations would feel different and require different responses. Confirmation that the filter is behind us would come from finding life, anywhere. Finding microbial life on Mars or in the oceans of Europa or Enceladus, or detecting biosignatures in the atmosphere of an exoplanet would immediately change the probabilistic assessment. If life arose independently on Mars and on Earth within the same solar system, it arose easily. If life arose easily, the biological steps of the Drake equation are not the filter. The filter must sit later, in the transition to intelligence or in the lifespan of civilizations. If the transition to intelligence were also found to be common, if we detected signals from multiple civilizations at various stages of development, the filter would have to sit even later, specifically in the lifespan variable, which would make the great filter almost certainly an ahead-of-us filter, which would mean every civilization that reached our level has subsequently failed. The discovery of life elsewhere, paradoxically, would be cause for concern rather than celebration in the context of the Fermi paradox. The easier life turns out to be, the more the silence implicates the later stages, and the later stages are the ones we are currently in. Nick Bostrom, the philosopher who has written extensively about existential risk, formalized this intuition. He argued that finding microbial life on Mars would be, in a specific sense, the most alarming possible result of any space mission. Not because the life itself is threatening, but because of what it would imply about the location of the filter. A sterile Mars suggests the filter is early, perhaps in the origin of life itself, and we have already passed it. A biologically active Mars suggests the filter is late, and we have not. This is a deeply counterintuitive conclusion. Most people would find the discovery of life on Mars thrilling and hopeful. In the context of the Fermi paradox, it should make us ask very hard questions about what happens to civilizations that are as advanced as we are. We have not found life on Mars. We have not found biosignatures in any exoplanet atmosphere. Every candidate has either been ruled out or remains statistically ambiguous. We have found no signals from any civilization at any stage of development. In Bostrom's framework, this null result is the most optimistic possible outcome of the search so far. Every nothing found is tentative evidence that the filter might be early. Every confirmation of extraterrestrial life would move the filter later. The silence is, in this reading, the best news we have, which does not make it less strange and does not make the implications less demanding. Let us now talk about something that takes the discussion from the cosmic to the immediate, about what the existence of the Fermi paradox and the evidence of filters ahead of us implies for what any individual alive right now should think about the future. The Fermi paradox is usually presented as a question about astronomy, a puzzle about why the sky is quiet. But its implications extend far beyond astronomy into questions about what happens to technological civilizations as a class, and what the odds are that we survive the transitions that appear to have ended or silenced so many others. We are inside the window, not outside it looking in, inside it. The processes that the data suggests are responsible for the silence, the rapid emergence of powerful artificial intelligence, the demographic decline following industrial prosperity, are not historical events we can study from a distance. They are ongoing developments we are participating in right now. The artificial intelligence systems that Garrett's model identifies as potentially civilizational scale disruptors are not hypothetical. They exist. They are improving rapidly. The governance frameworks for managing them are developing more slowly than the technology itself, which is precisely the dynamic Garrett's model identifies as dangerous. The demographic trends that Dugan's model identifies as potentially civilizational scale threats are not projections, they are current measurements. South Korea's fertility rate is 0.72 right now. Japan's is 1.2. Every major industrial economy is below replacement, and the trend is accelerating. These are not distant risks, they are present realities. The silence says that civilizations that reach this point usually do not persist long enough to become detectable from interstellar distances. Whether that outcome is inevitable, whether it is a thermodynamic property of intelligence, as Dugan suggests, or a governance failure that could in principle be avoided, or something else entirely, is the most important open question implied by the data. We cannot answer it from the data we have. The sample size of one, our own civilization, is too small to draw strong conclusions about what is possible versus what is probable. The silence tells us about the distribution of outcomes across many civilizations, but not about which point in that distribution we will occupy. What we can say is this: a civilization that understands the Fermi paradox, that takes seriously the evidence the silence provides about what happens to civilizations at our stage, that treats the filter question as empirically important rather than philosophically abstract, that civilization has at least the option of doing something differently than the civilizations that went quiet before it. The option is not a guarantee. Understanding a cliff does not mean you will not walk off it, but not understanding it removes the possibility of choosing a different path. The silence is the universe telling us something about ourselves, about what the end point of the trajectory we are on looks like, repeated across hundreds or thousands of independent trials, across billions of years of cosmic time. The message is not comfortable, but it is specific, it is measurable. It is derivable from 65 years of data collected by the most sensitive instruments human civilization has built, pointed at a universe that appears to contain the conditions for intelligence everywhere and the persistence of intelligence almost nowhere. That is the horror the silence contains. Not the terror of something coming for us from outside, the recognition that the silence is made of civilizations like ours, civilizations that asked the same questions, built the same instruments, pointed them at the same quiet sky, and then went quiet themselves. Not with a bang, with a measurement, and the measurement converging toward zero. Let us talk about something that almost never appears in discussions of the Fermi paradox, but that follows directly from what the silence implies, about what it means to be the civilization doing the searching rather than the civilization being searched for, and why our position in this investigation is not neutral. We are not external observers of the Fermi paradox, we are data points within it. Every discussion of why the sky is silent treats the question as though the questioner stands outside the phenomenon being investigated, as though we are scientists examining a sample that does not include us. But we are inside the sample. We are exactly the kind of civilization whose behavior and trajectory and eventual fate is being statistically described by the models we use to analyze the silence. When Garrett's model says civilizations have approximately 200 years between first radio transmission and fundamental transformation by artificial intelligence, that model includes us. When Dugan's model says civilizations experience irreversible demographic decline following industrialization, that model describes a process currently measurable in every industrialized nation, including every nation that funds SETI research. The investigators and the investigated are the same entity. This creates a specific epistemological problem. We are trying to understand the silence using reasoning faculties that are themselves products of the same evolutionary and civilizational trajectory that the silence is apparently characterized by. The biases, limitations, and blind spots in that reasoning are exactly the biases, limitations, and blind spots that would lead a civilization to fail to recognize the mechanisms producing the silence until it is too late to respond to them. Consider how this looks from outside. An alien researcher, if one existed, studying the behavior of technological civilizations, might observe that these civilizations reliably develop sufficient self-awareness to ask whether they are alone, develop sufficient technology to search for an answer, and then consistently fail to take seriously the implications of the answer they receive. They treat the silence as an astronomical puzzle rather than as direct evidence about their own trajectory. They continue optimizing for short-term goals, economic growth, military capability, technological advancement, even as the data suggests these optimizations are accelerating the very dynamics that produce the silence. The failure to respond to the Fermi paradox appropriately, to treat the silence as the most important signal we have ever received about our own future, may itself be a feature of the filter rather than an accident of our particular civilization's choices. Let us make this more concrete. The silence has been known as a serious scientific problem since 1950, 75 years. In that time, the resources allocated to understanding it have been trivially small compared to the resources allocated to the processes the models suggest are dangerous. Global spending on artificial intelligence development currently runs into the hundreds of billions of dollars annually. Global military spending exceeds $2 trillion annually. Global spending on understanding what the silence implies for our civilizational trajectory, on SETI research, on existential risk analysis, on long-term civilizational planning, is measured in the tens of millions. The ratio is approximately 100,000 to 1 in favor of accelerating the processes the silence warns about over understanding those processes. This is not a criticism of any individual or institution. It is a structural observation about what civilizations optimize for when individual actors, pursuing individually rational goals, produce collectively irrational aggregate outcomes. The tragedy of the commons applied to civilizational timescales. Every company developing more capable artificial intelligence is responding rationally to competitive incentives. Every government declining below replacement fertility is composed of individuals making rational choices about the cost and benefit of reproduction in a high-cost economy. Every military organization developing more capable weapons is responding rationally to security pressures. The aggregate of all these individually rational choices may be the production of exactly the dynamics that the silence describes. This is the deepest form of the Fermi paradox's horror. Not that some external force destroys civilizations, but that civilizations destroy themselves, or transform themselves beyond recognition through the aggregate of individually sensible decisions that collectively produce outcomes nobody chose and nobody would endorse if they could see the full trajectory. Let us now talk about something that is concrete and near-term, about specific predictions that follow from the models we have discussed, and whether those predictions are being tested by current data. Garrett's model predicts that civilizations spend approximately 1 century in the leaky electromagnetic phase, broadcasting unintentionally at detectable power levels, before either developing artificial general intelligence or becoming electromagnetically quiet through technological efficiency. The prediction can be tested on our own civilization. Earth began unintentional electromagnetic broadcasting approximately in the 1920s with the proliferation of broadcast radio. Military radar, the loudest signal Earth has produced, emerged in the 1940s. The electromagnetic footprint of Earth peaked somewhere in the mid to late 20th century and has been declining since. Streaming replaced broadcast television, fiber replaced wireless, compressed digital signals replaced analog. The trajectory of Earth's electromagnetic visibility is already consistent with Garrett's model. We are getting quieter. Within decades, our unintentional electromagnetic leakage may fall below any realistic detection threshold for instruments outside the solar system. Simultaneously, the development of artificial intelligence is accelerating. The transition from narrow, task-specific AI to systems capable of general reasoning has been happening faster than most researchers predicted 5 years ago. Whether this constitutes the kind of fundamental civilizational transition that Garrett's model identifies as the filter mechanism is not yet clear, but the timeline is consistent with his 200-year estimate. We are approximately 127 years into the electromagnetic window. Duggan's model predicts that fertility decline is irreversible once industrial prosperity reaches a sufficient level, that the decoupling of reproduction from survival is thermodynamic rather than contingent on policy choices. This prediction can also be tested on current data. South Korea has been below replacement fertility since the 1980s. 40 years of various government interventions, financial incentives, expanded parental leave, subsidized childcare have not reversed the trend. The fertility rate has continued falling even as the intensity of pronatalist policy has increased. The 2024 fertility rate of 0.72 is the lowest ever recorded for a major nation. Japan has been below replacement for longer. Italy, Germany, Spain, Portugal, every wealthy European nation have been below replacement for decades. The trend shows no sign of reversing in any of them, regardless of policy environment. Duggan interprets this as evidence that the mechanism is not policy contingent. That once a population reaches a sufficient level of individual autonomy and economic development, the decline becomes self-sustaining and self-accelerating through the age structure effects. A declining cohort of young people produces fewer parents, which produces a still declining cohort, compounding downward regardless of external intervention. The prediction is that this trend, absent some discontinuous social or technological change that has not yet been demonstrated anywhere, will continue. That the peak of human population around 2080 will be followed by a decline that accelerates with each generation. Whether discontinuous change is possible, whether some development in reproductive technology or some cultural shift, or some restructuring of economic incentives sufficiently radical to reverse the mathematics, is the critical, uncertain variable. No existing evidence suggests such a reversal is underway anywhere. Both sets of predictions are consistent with current data. Neither is falsified. Both describe trajectories that are already moving in the directions the models indicate. This is what makes the Fermi paradox not merely academically interesting, but practically urgent. The models that explain the silence make specific predictions about our own civilization's near-term trajectory. Those predictions are currently being confirmed by the data. Let us now talk about what the specific history of false positives in SETI research tells us. Not about extraterrestrial civilizations, but about the cognitive and psychological tendencies of the civilization doing the searching. Every significant SETI false alarm has followed the same pattern. An anomalous signal appears. Initial analysis cannot identify a mundane explanation. Scientific excitement grows, carefully contained in public but real in private among the researchers involved. Further analysis eventually identifies a natural explanation that nobody had predicted. The excitement collapses. The candidate is added to the list of things that almost were. Pulsars in 1967, the WOW signal in 1977, the Dyson sphere candidates in 2024, BLC1 in 2020, dimethyl sulfide on K2-18b in 2023. In every case, the universe produced something that looked designed and turned out to be natural. In every case, the natural explanation was something that researchers had not anticipated: rotating neutron stars, magnetar-triggered hydrogen maser flares, background galaxy contamination, local radio frequency interference, atmospheric chemistry. The pattern suggests something important about the universe's capacity to produce phenomena that mimic intelligence at exactly the frequencies, power levels, and behavioral signatures that we would expect from an artificial source. It also suggests something about our cognitive tendency to find patterns that confirm what we are looking for. Every one of these false positives was initially evaluated by researchers who desperately wanted to find a genuine signal. Every one passed initial scrutiny, not because the scrutiny was inadequate, but because the mimicry was sufficiently precise to fool sophisticated instruments and trained scientists. The universe is, in a specific sense, actively deceptive, not through any intention, but through the sheer variety of natural processes it can produce. For every detection threshold we set, the universe appears to have natural phenomena that can cross it. This raises a question that sits beneath the entire enterprise of SETI. How would we know if we found a real signal? What evidence would be sufficient to distinguish a genuine artificial transmission from a sufficiently exotic natural phenomenon? The current consensus is that a confirmed detection would require simultaneous independent observation by multiple instruments on different continents, reproducibility across observation sessions, frequency behavior inconsistent with any known natural source, and information content demonstrable as structured rather than random. BLC1, the strongest recent candidate, failed most of these criteria when examined carefully. The WOW signal would potentially pass some of them. Its frequency and power behavior remained genuinely difficult to explain naturally, but it was never reproduced, and the instrument that detected it was demolished before modern follow-up was possible. The most honest answer to how we would recognize a real signal is that we are not entirely sure. The history of false positives suggests that the recognition problem is harder than it initially appeared. And the possibility that we have already received genuine signals that we dismissed as natural phenomena, or that we received them before the technology to recognize them existed, cannot be excluded. Let us now talk about something that requires a specific kind of imagination, about what the discovery of a genuine signal would actually feel like, not in the abstract, but as a lived experience for the civilization receiving it, and what it would immediately imply. Imagine the moment of confirmation. Not the initial detection. Initial detections have happened many times, and each time has been eventually explained away. But the moment when a signal has survived every filter, been confirmed by multiple independent instruments, shown demonstrable information content, been verified against every known natural source, and been determined with high confidence to be artificial. The immediate scientific implication is not comforting. A confirmed artificial signal means the filter is not in the early biological stages, because this civilization made it past those stages. It means intelligence is not uniquely rare, because this civilization developed it. It means something about our own filter question has been answered, and the answer moves the filter later. If the signal comes from a civilization at approximately our own technological level, early radio, comparable to where Earth was in the mid-20th century, then the filter question becomes, what happened to them between then and now? Are they still broadcasting? Have they gone quiet? Have they expanded? The answers to these questions, derivable from detailed analysis of the signal, would be among the most important data points in human history. If the signal comes from a civilization significantly more advanced than us, producing energy at scales consistent with a Kardashev Type 2 or higher civilization, then the filter question becomes, how did they survive to that point? What did they do differently? What specific transitions did they navigate that our models suggest should have silenced them? Either way, the discovery does not resolve the Fermi paradox. It deepens it. It answers the question of whether intelligence exists elsewhere, while simultaneously raising the question of what happens to intelligence at the specific stages we are currently in. The discovery would also immediately trigger the question of whether to respond, the METI debate, which has been unresolved for decades and has no institutional framework for resolution. Who decides what Earth says? By what process? On what timeline? With what consideration for the possibility that responding is not in humanity's long-term interest? These questions have no established answers. There is no treaty, there is no protocol, there is no international body with the authority to decide on behalf of humanity what we say to a confirmed alien civilization. Individual researchers with access to sufficiently powerful transmitters can make that decision unilaterally, as Alexander Zaitsev demonstrated in 1999 when he broadcast from the Evpatoria radar in Crimea without consulting any international body. The governance gap exists. It has existed since the beginning of the space age. It has never been seriously addressed. And in the background of all of this governance confusion, the silence continues. FAST is still listening in Guizhou province. The 500-meter dish that replaced Arecibo as the world's most sensitive single-aperture radio telescope is working through the 100 candidate signals that survived 21 years of SETI at home processing. Signals that emerged from 12 billion candidates and could not be classified as terrestrial interference. One by one, FAST is re-observing each at higher sensitivity than any instrument that preceded it. As of early 2026, none of the re-observed candidates has produced a confirmed repeat detection. The James Webb Space Telescope continues analyzing exoplanet atmospheres during transit events, building up signal over multiple observations of each target. The oxygen discovery in the Pacific Deep Ocean has complicated the interpretation of atmospheric oxygen as a biosignature. The dimethyl sulfide detection on K2-18b has not been confirmed by independent analysis. No exoplanet has a confirmed atmospheric biosignature. The Breakthrough Listen program is processing data 600 times faster than 5 years ago, using machine learning algorithms that can sift through radio telescope observations at speeds impossible for human analysts. The accelerated processing has not changed the output. More data, processed faster, produces the same number of confirmed artificial signals as slower processing of less data. The silence is not a function of instrument sensitivity or processing speed or search coverage. It is robust across every dimension in which the search has been expanded. Let us now talk about something that the Fermi paradox implies about the structure of knowledge itself, about what it means to ask a question for 75 years and receive only one answer, and what that means for how we should treat the question going forward. Science progresses most reliably when experiments can be repeated, when alternative hypotheses can be tested, when the sample size is sufficient to distinguish signal from noise. The search for extraterrestrial intelligence violates several of these norms in ways that make it one of the most epistemologically unusual scientific programs ever conducted. The sample size of confirmed detections is 0. The sample size of civilizations we can directly observe the trajectory of is 1, our own. Every model of what happens to technological civilizations is built on a sample of one data point, extrapolated across a null result. This is not a criticism of SETI as a scientific enterprise. The question is too important to abandon simply because it is epistemologically difficult. But it means that the conclusions we can draw from the data are less certain than they would be in any field with larger samples. What we can say is that the silence is inconsistent with a universe containing many long-lived detectable civilizations. What we cannot say with certainty is which specific aspect of the development chain is responsible for their absence. Early biological rarity, late civilizational brevity, deliberate silence, or some combination. The most honest scientific position is that the silence is real, that it is a measurement rather than an absence of data, that it constrains the space of possible explanations substantially, and that the most likely explanations place the dominant filtering mechanism either in the extreme rarity of the path from chemistry to intelligence, or in the extreme brevity of the period during which intelligence produces detectable signals. Both of these explanations have direct implications for our own trajectory. The rarity explanation suggests we are extraordinarily unusual, and our continued existence has outsized cosmic significance. The brevity explanation suggests we are on a trajectory that, historically, has almost always produced silence within centuries of its current stage. Neither is comfortable. Neither is falsified by current evidence. Both deserve to be taken seriously as inputs to decisions about how we invest resources, how we govern powerful technologies, how we think about the long-term continuity of our civilization. The Fermi paradox is not an astronomical puzzle waiting for a better telescope. It is a mirror pointed at what we are becoming, reflecting a pattern derived from a universe that has run this experiment many times and recorded the results in the form of silence. The results say something. The question is whether we are capable of listening. Let us now talk about what happens at the boundary of what the data can tell us, about where the scientific investigation of the silence ends and the philosophical implications begin, and why the transition between these two domains is less clean than it usually appears. The scientific investigation can establish that the silence is real, that after 65 years and billions of candidate signals, the number of confirmed artificial extraterrestrial detections is 0. It can constrain the number of detectable civilizations in the Milky Way to fewer than 1 to 5 per century. It can identify specific mechanisms, the 200-year AI window, the demographic decline following industrialization, that are consistent with producing the observed silence. It can rule out certain explanations. The universe is not full of civilizations broadcasting loudly at radio frequencies in our neighborhood. What the scientific investigation cannot establish is what we should do with this information, whether the brevity of civilizations is inevitable or contingent, whether the filter mechanisms are navigable, whether our civilization's trajectory is fixed or malleable, whether the silence should produce despair or urgency, or some specific reorientation of priorities. These are questions that the data bears on but cannot answer. They require philosophical and ethical reasoning applied to the empirical constraints the data provides. And this is where the investigation becomes personal in a way that purely astronomical questions do not. The Fermi paradox is ultimately a question about what we are and what we are becoming, and whether what we are becoming tends to persist or to vanish. It is a question that the universe has answered, in aggregate, across many samples, and the answer is silence. The philosophical task is to understand what that answer implies for the one sample we can actually observe from the inside. The answer is not nothing. The answer is not despair, but it is not comfortable either. It is a specific, quantifiable, empirically grounded statement that civilizations like ours, civilizations that have reached the stage of asking, "Where is everybody?" and building instruments to search for an answer, are almost certainly not the typical outcome of the universe's capacity to produce intelligence. And if they are not the typical outcome, then whatever we are and whatever we might become is not a foregone conclusion written into the structure of the cosmos. It is something that has to be built, maintained, chosen, against the grain of processes that, historically, have almost always won. That is what the silence contains. That is what 65 years of null results, 12 billion processed candidates, 74 million narrowband hits from an interstellar visitor, and the demolished telescope on the Ohio golf course are actually saying. The universe is full of opportunities for intelligence. Intelligence does not reliably take them. The question is whether this particular instance of intelligence, the one doing the searching, the one asking the question, the one reading these numbers and feeling the specific weight of them, is capable of being the exception. The instruments are still running, FAST is still listening. James Webb is still analysing atmospheres. The algorithms are getting faster. The searches are getting larger. The number has not changed. And somewhere in that unchanged number is everything important about what happens next. Let us talk about something specific that illuminates the silence from an angle rarely examined, about what the universe's age distribution of stars implies for the timing of intelligence, and why the arithmetic of when civilizations could have arisen produces a conclusion more disturbing than most treatments acknowledge. The Milky Way has been forming stars for approximately 13.6 billion years. But not all stars are equally useful for the development of complex chemistry and biology. The earliest generations of stars, population 3 stars, formed from the primordial hydrogen and helium of the Big Bang, were metal poor. They lacked carbon, oxygen, nitrogen, silicon, and the other heavier elements that organic chemistry requires. These first stars lived fast and died violently in supernovae, seeding the interstellar medium with the heavier elements that the next generation would incorporate. By approximately 9 to 10 billion years ago, stellar populations sufficiently enriched in heavy elements to support rocky planet formation and organic chemistry were becoming common. This is the earliest plausible window for the development of life as we understand it anywhere in the Milky Way. Our solar system formed approximately 4.6 billion years ago, meaning it formed when the galaxy was already 9 billion years old. We are not early. We are not the first generation of potentially life-supporting systems. We formed in the middle of the galaxy's metal-enriched history. There were billions of years of potential biological opportunity before our solar system existed. If any planet in the galaxy developed intelligent life 2 billion years before Earth did, and there is no known reason why this is impossible, that civilization has had 2 billion years of technological development ahead of ours. To put this in perspective, 2 billion years ago on Earth, the most complex organisms were single-celled eukaryotes. The entire history of multicellular life, of animals, of vertebrates, of mammals, of primates, of humanity, of every technological achievement in human history, all of it fits inside a 600 million year window. A civilization with 2 billion years of technological development has had time to complete that entire arc more than 3 times over. What would 2 billion years of technological progress look like? We cannot imagine it. The honest answer is that we cannot imagine it. We can extrapolate from our own trajectory, 100 years from first radio to sophisticated AI, exponential improvement in computing capability, increasingly precise control over matter at molecular and atomic scales. But extrapolating 2 billion years of continued development from that starting point produces numbers and capabilities that have no meaningful description in any framework we currently possess. A civilization 2 billion years ahead of us in technological development would bear the same relationship to us that we bear to the bacteria living in the early Proterozoic ocean. We cannot model what they want, how they think, what they would build, or how they would interact with the universe around them. The assumption that such a civilization would produce detectable radio signals or infrared waste heat from Dyson spheres, the signatures we have been searching for, may be as naive as a bacterium assuming that technologically advanced organisms would produce exactly the kinds of chemical signals that bacteria use to communicate. There are hundreds of millions of stellar systems in our galaxy that are significantly older than ours and have had metal-enriched chemistry available for longer. The existence of even one civilization that crossed the threshold of technological development before ours and has been developing for millions of years should leave traces visible across the galaxy, unless those traces are invisible to instruments designed around our current understanding of what technology looks like. This is the most unsettling version of the silence. Not that nobody developed intelligence before us, but that somebody did, perhaps many somebodies, and what they subsequently became is so far outside our conceptual framework that we cannot recognize the traces they left. The universe around us might be saturated with the products of 2 billion-year-old technologies that we interpret as natural phenomena, because our instruments and our theories have no framework for distinguishing them from nature. Dark matter, dark energy, the specific values of physical constants that appear fine-tuned for the existence of complex chemistry, the large-scale structure of the universe. Any of these could be the products of engineering at scales so far beyond our current capability that we have no way to identify them as artificial. We would explain them with physics, and we would be correct that they follow physical laws, without recognizing that following physical laws does not preclude being engineered. This is the limit of what the silence can tell us. At a certain level of technological development, the distinction between the natural and the artificial may become undetectable from a position as primitive as ours. The universe may have been modified in ways we cannot recognize as modifications. The silence may not be a silence at all. It may be a conversation happening in a medium we have not yet conceived of, between entities we cannot conceptualize, about subjects that our current cognition is not equipped to represent. Or the silence may be exactly what it appears to be, emptiness, the product of intelligence being rare and brief and leaving no durable trace. Both interpretations are consistent with the data. Neither can currently be distinguished from the other with instruments we possess. Let us now talk about something that is more bounded and more specific, about the concrete decisions being made right now that will determine whether our own civilization produces a signal that any future observer would classify as having persisted or as having gone quiet. The two filters identified by Garrett and Duggan are not symmetric in their urgency. Demographic decline, Duggan's mechanism, operates on timescales of generations. It is slow enough to potentially allow for response if the response is sufficiently early and sufficiently large. Artificial intelligence, Garrett's mechanism, operates on timescales of years to decades. The window for governance responses to the AI transition is narrowing faster than the institutional capacity to implement those responses is developing. This asymmetry matters enormously for what the silence implies we should do right now. The demographic filter, if it operates as Duggan's model suggests, requires intervention at the level of restructuring the economic incentives that make reproduction feel costly rather than beneficial. This is not a technical problem. It is a coordination problem of enormous scale, involving the restructuring of economic systems, housing markets, labor markets, and social support systems in ways that make raising children economically compatible with individual prosperity, rather than a competing claim on individual resources. No government has successfully implemented this restructuring. The closest attempts, Scandinavia's extensive family support systems, have produced above-average fertility rates for wealthy nations, but still below replacement. The gap between where fertility rates are and where they would need to be for population stability is not a gap that incremental policy adjustments appear capable of closing. Whether it is closable at all is genuinely uncertain. Duggan treats it as thermodynamically fixed. Others argue that sufficiently radical restructuring of economic and social systems could reverse the trend. The evidence currently available does not distinguish between these positions with high confidence. The artificial intelligence filter, if it operates as Garrett's model suggests, requires governance structures capable of managing the development of systems more cognitively capable than the humans managing them. A bootstrapping problem without obvious precedent in human institutional history. Every previous technology that humans have governed was less capable than humans in the specific domains relevant to its governance. Nuclear weapons required physics expertise to govern, but did not require the weapons themselves to be smarter than the physicists regulating them. Artificial general intelligence, systems capable of the kind of general reasoning and planning that previously only human cognition could perform, represents the first technology where the thing being governed may be more capable at governance-relevant reasoning than the humans doing the governing. This creates a specific and novel challenge that existing institutional frameworks were not designed to address. The people working on this problem within AI safety research and policy recognize its difficulty. Progress is being made, but the speed of capability development in AI systems has consistently outpaced the development of governance frameworks, not because the governance work is not happening, but because the capability development is happening faster. If Garrett's model is correct, if the window between first detectable electromagnetic emission and fundamental civilizational transformation by AI is approximately 200 years, we are at approximately the midpoint of that window. The time available for developing adequate governance frameworks is not centuries, it is decades. These are not abstract future concerns. They are present decisions being made by specific institutions and specific individuals about specific technology development trajectories and specific policy frameworks. The silence that 65 years of SETI research has produced is evidence about the distribution of outcomes when civilizations reach this point. The outcome distribution appears heavily weighted toward going quiet. Whether we are capable of being the outlier in that distribution is the most important empirical question of our time. Not because the Fermi paradox is the most important scientific mystery, though it is significant, but because the answer has direct implications for whether the civilization conducting the search continues to exist in a form capable of eventually receiving an answer. Let us now talk about something that brings the entire discussion into the most immediate possible focus, about what it means to live in the window that the silence describes, and how the knowledge of what that window typically produces should change the experience of being alive in it. There is a specific kind of double consciousness that the Fermi paradox produces in anyone who thinks about it carefully. On one level, daily life proceeds normally. Economic decisions are made, relationships are formed, careers are pursued. The ordinary texture of human experience continues largely unaffected by questions about interstellar silence. On another level, the knowledge of what the silence implies sits in the background as a constant, low-frequency signal. The awareness that we are inside a window that historically produces silence, that the processes producing that silence are identifiable and ongoing, that the civilization we are part of is navigating a transition that analogous civilizations appear to have failed to navigate. These two levels of experience are genuinely difficult to hold simultaneously. The ordinary urgencies of daily life are immediate and visceral. The civilizational urgencies implied by the Fermi paradox are abstract and long-term. Human cognition is well calibrated for the former and poorly calibrated for the latter. We evolved to respond to immediate threats, not to century-scale trajectories. This calibration mismatch is itself a potential contributor to the filter mechanism. A civilization that produces the intelligence necessary to understand the Fermi paradox also produces cognitive architecture poorly suited to responding to what it implies. The self-awareness and long-term reasoning capacity required to recognize the danger are present. The emotional and motivational systems required to act urgently on long-term abstract risks are systematically underdeveloped relative to the systems driving immediate consumption, reproduction, status-seeking, and tribal competition. This may not be accidental in an evolutionary sense. The cognitive features that make it difficult to respond appropriately to the Fermi paradox are the same features that conferred reproductive fitness in the environments in which human cognition evolved. There was no selection pressure for the ability to respond urgently to century-scale civilizational risks, because such risks did not exist in environments where human cognitive architecture was being shaped. We are using minds built for the Pleistocene to navigate the Anthropocene's civilizational challenges. The mismatch between the intelligence required to identify the problem and the motivational architecture required to respond to it adequately may be structural rather than contingent, a feature of what intelligence looks like when it first emerges from biological evolution rather than a feature we could have avoided. Whether this mismatch is navigable, whether intelligence can be directed to override its own evolutionary calibration at civilizational scale, is one of the questions the silence cannot answer from the outside. It can only be answered from the inside by a civilization actually attempting the navigation. We are that civilization, right now. The navigation is not hypothetical or future, it is ongoing. Let us now talk about something that is both the most hopeful and the most ambiguous aspect of the entire Fermi paradox, about the possibility that the filter is genuinely behind us, and what following that possibility honestly implies. The most optimistic resolution of the Fermi paradox, the one that, if true, would mean the silence is expected rather than alarming, is that the origin of life is extraordinarily rare, that the chemical transition from non-living matter to self-replicating biology, while it happened quickly on Earth, is so improbable that it has happened nowhere else, or almost nowhere else, in the observable universe. If this is true, then the silence is simply the expected result of a universe where biology is a 1 in a trillion accident. We are alone, or nearly alone, not because civilizations fail, but because life never starts. The filter is behind us, not just partially, but almost entirely. We passed the hardest step. Everything that follows is comparatively easy by probability. This interpretation is not supported by current understanding of abiogenesis. The evidence from Earth suggests that life appeared essentially as soon as conditions permitted, not after billions of years of failed chemical experimentation, but within the first few 100 million years of planetary habitability. The 2023 to 2025 research showing that amino acids and RNA nucleotides likely co-evolved together rather than appearing sequentially makes the origin of life look more robust and chemically probable than the RNA world hypothesis alone implied. A fast, robust, multi-pathway origin of life on Earth is evidence against the interpretation that abiogenesis is extraordinarily rare. It is evidence, not proof, but evidence, that life starts wherever conditions allow, which means the silence cannot be primarily explained by life being rare. But we have only one data point: Earth. One instance of abiogenesis in one location at one time. You cannot derive reliable statistics about the frequency of an event from a single observation of it, especially when the observer's existence is conditional on the event having occurred. We would not be here to observe the universe if life had not started on Earth. So the fact that it started on Earth and started quickly cannot tell us by itself how often it starts elsewhere. The anthropic selection effect, the fact that observers necessarily find themselves in universes where the conditions for their existence were met, makes it impossible to distinguish between two scenarios using only self-referential data. In scenario 1, life starts easily everywhere and the universe is biologically active at massive scale. In scenario 2, life is extraordinarily rare and we happen to be in one of the few places where it started. Both scenarios produce the same observation from our vantage point. We find ourselves on a life-bearing planet. The only way to distinguish between these scenarios is to look elsewhere, to search for life on Mars or Europa or in the atmospheres of exoplanets. If life is found elsewhere, if it started independently in another location, the easy start interpretation gains enormous support. The universe is biologically active. The filter is not in abiogenesis. If life is not found elsewhere despite extensive search, if Mars is sterile, if Europa's ocean has no biology, if exoplanet atmospheres show no biosignatures after decades of observation, the rare start interpretation gains support. Life may be a genuine cosmic lottery winner, present on Earth and perhaps almost nowhere else. Current data does not resolve this. Mars exploration has not confirmed the presence or absence of past or present life. Europa and Enceladus have not been directly sampled for biology. Exoplanet atmospheric characterization is in its early stages, and no confirmed biosignature exists. The investigation is ongoing. The question is open, and the answer, whichever way it falls, will be the most important finding in the history of science. more important than relativity or quantum mechanics or the structure of DNA, because it will tell us where in the chain of development from chemistry to civilization the hardest transition sits, and by implication, whether what is ahead of us is navigable or whether it is the wall that stops everyone. Let us now talk about what happens if the silence continues, about what a world looks like in which we search for another 50 years and find nothing, and what that extended null result would mean. If the James Webb Space Telescope completes its operational lifetime without confirming a biosignature in any exoplanet atmosphere, if its successor instruments similarly return null results, the probability of the early filter interpretation increases substantially. A universe where a telescope capable of detecting biosignatures in dozens of nearby exoplanet atmospheres finds nothing after decades of searching is a universe where life is genuinely rare. If FAST completes its re-observation of the 100 surviving SETI at-home candidates and finds no confirmed artificial signals, if the next generation of radio telescopes, more sensitive by another order of magnitude, scans millions more stars and finds nothing, the probability of the early filter interpretation increases further. Or alternatively, the probability that detectable civilizations are genuinely brief increases. If Mars Sample Return, the program to bring Martian rock and soil samples back to Earth for analysis, finds no evidence of past or present biology after thorough examination, the early filter interpretation gains its strongest support yet. Each null result is a tightening of the constraint. Each failed search in a larger and more sensitive program narrows the space of possible explanations and increases the weight of evidence on whichever explanation is consistent with continued silence. A world in which 50 more years of searching produces nothing will be a world in which the Fermi paradox is no longer a puzzle requiring a solution. It will be a world in which the silence is understood as a fundamental property of the universe. Life is extraordinarily rare, or intelligence is extraordinarily brief, or both. And the implications of that property for how we understand our own situation will be impossible to avoid. That world will have to reckon with what the silence means for the value of what we are and what we are building. If we are among the very few intelligent civilizations that have ever existed in the observable universe, then every work of human knowledge and culture and understanding is cosmically unique in a way that purely philosophical arguments for its value cannot establish. The loss of this civilization would not be merely a tragedy for the beings within it. It would be a reduction in the total amount of understanding that has ever existed in a universe that appears to produce understanding extraordinarily rarely. This is not a comfortable thought, but it is a thought that the silence implies, and the silence is a measurement. Let us now talk about something that is concrete and immediate and personal, about what any individual living right now can do with the knowledge that the silence provides, and why the answer to this question is less obvious than it might appear. The Fermi paradox does not provide a clear action agenda. It does not say stop developing AI or have more children or change specific policies. It says that civilizations like ours appear to go quiet within centuries of reaching our current stage, that the mechanisms responsible for this appear to be identifiable and already active, and that the history of the universe suggests these mechanisms almost universally prevail. What any individual does with this information is not determined by the information itself. It depends on values, on circumstances, on the specific domains in which any individual has capacity to act. But there are a few things the Fermi paradox does suggest with reasonable specificity. First, it suggests that taking long-term civilizational continuity seriously, as a genuine priority rather than an abstract concern, is reasonable. The silence is evidence that civilizations at our stage typically fail to achieve it. Treating the continuation of this civilization as important and fragile rather than as a default background condition is epistemically appropriate given what the data shows. Second, it suggests that the specific mechanisms identified as filters deserve more resources and more serious governance attention than they currently receive. The ratio of resources devoted to developing powerful AI versus resources devoted to governing it safely is approximately 100,000 to 1 in favor of development. The ratio of resources devoted to identifying what the demographic trend implies and responding to it versus resources devoted to everything else is similarly imbalanced. These imbalances are not required by any physical law. They are products of incentive structures that could, in principle, be restructured. Third, it suggests that the search itself should continue, not because the silence is about to break, but because what we find or fail to find is direct evidence about our own situation. Every confirmed instance of extraterrestrial life moves the filter later and makes the ahead-of-us explanations stronger. Every extended null result in biosignature searches moves the filter earlier and makes the behind-us explanations stronger. The information is directly relevant to understanding what we are and what trajectory we are on. Fourth, and perhaps most importantly, it suggests that the specific combination of intelligence and self-awareness that allows us to ask these questions and understand the data has enormous potential value that extends beyond any individual or any generation, to the possibility that a form of intelligence capable of understanding the universe has managed to persist and grow when the universe's history suggests it almost never does. That possibility is not guaranteed. The silence is evidence against it. But possibility is not the same as probability, and the silence, while it constrains the distribution of outcomes, does not fix our position within that distribution. We are still inside the window. The instruments are still running. The question is still open. And the specific quality of attention we bring to the question, the seriousness with which we treat what the data says about our situation, the resources we allocate to understanding and navigating the filters the data identifies, the degree to which the individuals and institutions making consequential decisions take seriously the cosmic context in which those decisions are being made, is itself a variable that the silence does not determine for us. It is the one variable left open. Let us now talk about something that is both the oldest and the most current thread in this entire discussion, about why the question Fermi asked at a lunch table in 1950 is more urgent now than it was then, and what has changed between 1950 and now that makes the silence more informative and more pressing. In 1950, when Fermi asked, "Where is everybody?" the silence was not yet a measurement. It was a logical puzzle. The instruments to search for a signal barely existed. The first deliberate SETI search was a decade away. The knowledge that planets were common around other stars did not exist. The first confirmed exoplanet would not be detected for another 42 years. The understanding that life appears quickly on habitable planets was not established. The dating of early terrestrial microfossils and molecular evidence for Luca at 4.2 billion years ago came much later. Fermi's question in 1950 was a puzzle based on reasoning alone. The universe is old and large and should have produced many civilizations if intelligence arises with any regularity. Where are they? Now it is more than a puzzle. It is a measurement problem. We now know that planets are essentially universal around stars. We now know that life started fast on Earth. We now know that the chemical building blocks of life, amino acids, nucleotides, complex organic molecules, are found throughout the interstellar medium, in comets, in meteorites, in molecular clouds far from any star. We now know that the universe has had 8 to 9 billion years of metal-rich stellar chemistry, time for the experiment to have run thousands of times. And we have now searched, systematically, with instruments orders of magnitude more sensitive than anything available in 1950, across a wide range of frequencies and search strategies, and found nothing. The silence in 1950 was a theoretical expectation of noise that had not yet been confirmed. The silence in 2026 is 65 years of accumulated null results from the most sensitive search ever conducted for the most unambiguous signatures of technological activity. The question has not changed. The weight of evidence bearing on it has increased by many orders of magnitude, and the evidence keeps pointing the same direction. Something is happening to civilizations between the moments they first become possible, when chemistry turns into biology and biology turns into intelligence, and the moments they would need to persist for us to find them. Something systematic, something almost universal, something that operates with enough consistency across enough independent instances that the 13.6 billion year history of our galaxy has produced, as far as 65 years of increasingly sensitive searching can determine, no persistent detectable civilization other than our own. Whatever that something is, we are in it right now. The artificial intelligence developing faster than its governance. The fertility rates falling below replacement in every industrialized nation. The electromagnetic window closing as technology advances. The institutions funding the search being demolished for golf courses and defunded by single Senate votes. These are not separate phenomena. They are aspects of a single trajectory, the trajectory that civilizations like ours follow when they reach this stage of development. The trajectory that the silence suggests almost always ends the same way. Fermi asked, "Where is everybody?" The answer the data supports is, they were here, they went through what we're going through, and they went quiet. Not all of them, and not necessarily forever, but most of them, and usually within centuries of reaching the stage we are at now. The instruments are still running, the window is still open. The question is still the most important one we have ever asked. And the silence has been answering it for 65 years. Go outside tonight and look up, not at anything specific, just at the sky, the dark between the stars. The specific quality of silence that has no sound to it, only the absence of one. That silence is not empty. It contains 65 years of accumulated measurement, 12 billion candidate signals processed by volunteer computers on millions of machines, 74 million narrowband hits from an object that arrived in our solar system from another star, 28 hours of continuous observation pointed at 7 rocky planets orbiting a red dwarf 39 light-years away. The largest Dyson sphere search ever conducted, covering 5 million stars. Every candidate resolved, every anomaly explained, every signal traced to noise or interference or a natural phenomenon nobody had predicted. The number at the end of all of it is 0. Not approximately 0. Not close to 0 with some promising candidates still under review. 0. Confirmed artificial extraterrestrial signals detected in 65 years of increasingly sensitive searching across dozens of independent programs using different instruments at different frequencies in different parts of the sky. 0. That number deserves to be held for a moment before any interpretation is applied to it. It is a measurement, one of the most carefully obtained measurements in the history of science, produced by the combined effort of thousands of researchers across dozens of countries over more than 6 decades. And it says something specific about the universe we live in. The universe is approximately 13.8 billion years old. It contains at least 2 trillion galaxies. Our galaxy alone contains somewhere between 200 and 400 billion stars. We now know from the Kepler Space Telescope's survey of 150,000 stars, from the statistical analysis that followed that virtually every one of those stars has planets. Roughly 40 billion of those planets in our galaxy alone sit in the temperature range where liquid water is stable on a surface. 40 billion potential homes for life in one galaxy out of 2 trillion. And life, when it starts fast. Earth formed 4.54 billion years ago. By 4.2 billion years ago, within the first few 100 million years, while the surface was still being bombarded by asteroids, while conditions were still violently hostile, something had crossed the threshold from chemistry to biology. The last universal common ancestor of all life on Earth existed before the planet had finished settling. Life did not require perfect conditions. It did not require a billion years of careful chemical experimentation. It emerged at the first opportunity. If that is true here, it is probably true elsewhere. The chemistry is not unique. The elements are not unique. The physics is the same everywhere. The 40 billion habitable worlds in our galaxy are running the same experiment that Earth ran 4.2 billion years ago. The experiment should be producing results. The sky is silent. This is the central fact from which everything else follows. Not a mystery to be solved by waiting for better instruments, a measurement that has been converging on the same answer for 65 years. A measurement that statistical models now translate into a specific constraint. Fewer than 1 to 5 detectable technological civilizations per century in the Milky Way galaxy. Per century. In a galaxy of hundreds of billions of stars, on a timescale of 13.6 billion years. Something is filtering them out. Not one thing, probably. A series of bottlenecks, each one severe enough to eliminate a significant fraction of everything that gets through the previous one. The origin of life may be one. The transition from single-celled to complex multicellular life may be another. Earth spent 2 billion years stuck at the single-celled stage before that transition happened. The emergence of intelligence capable of building technology may be another. And then there are the filters that sit ahead of us, the ones identified not by looking backward at what was difficult, but by looking at what the data says happens to civilizations that reach our current stage. Michael Garrett's model places one filter in the artificial intelligence transition. The window between a civilization's first detectable electromagnetic emission and its fundamental transformation by artificial intelligence is approximately 200 years. Not because AI is inherently destructive, but because the speed of capability development consistently outpaces the development of governance frameworks capable of directing it. The technology advances, the institutions capable of managing it do not advance at the same speed. The gap between them is where civilizations go quiet. We are 127 years into that window. Darren Dugan's model places another filter in the demographic mathematics of intelligence itself. When a species becomes sophisticated enough to model the future consequences of reproduction with enough fidelity, reproduction becomes a deliberate choice made against an honest accounting of its costs. In subsistence economies, children are labor. In wealthy technological economies, children are expensive. The individual calculus shifts. Fertility falls. Every industrialized nation on Earth is below replacement. South Korea is at 0.72, not half of replacement but 1/3. No government that has tried to reverse this trend has succeeded. The population peaks around 2080, then it falls. And the mathematics of falling populations accelerates with each generation because a smaller cohort of young people produces a still smaller cohort of parents. These two filters, Garrett's 200-year AI window and Dugan's demographic decline, are not predictions about a distant future. They are descriptions of processes currently underway and currently measurable in the data of our own civilization. We are inside both of them. The silence is the aggregate result of both processes, and probably others we have not yet identified, operating across hundreds or thousands of independent civilizations over 13.6 billion years of cosmic time. The result of all those experiments, run independently across all those star systems across all that time, is the number we keep measuring: 0. The most terrible thing about that number is not what it says about other civilizations. It is what it says about us, about where we are in the trajectory that the silence describes, about what the universe's accumulated experimental record suggests happens to intelligence at the specific stage of development we are currently in. The Fermi paradox is usually presented as a question about astronomy, as a puzzle about whether we are alone, as an interesting intellectual problem for researchers with radio telescopes and statistical models. It is all of those things, but it is also something more immediate. It is a mirror pointed at what we are becoming, at the processes we have set in motion, at the speed mismatch between our technological capability and our institutional wisdom, at the demographic mathematics unfolding in every hospital maternity ward in every wealthy country on Earth, at the electromagnetic window closing quietly as our technology advances. The mirror does not show us our fate. The distribution of outcomes that the silence describes is a distribution, not a fixed point. Every distribution has outliers. Every historical pattern has exceptions. The silence tells us what usually happens. It does not tell us what must happen, but it tells us what usually happens with unusual precision. 65 years of searching, billions of candidates, a universe 13.8 billion years old with every opportunity to fill itself with intelligence. And the measurement that emerged from all of it is the same measurement every year: 0. There is a telescope in Guizhou province in China, 500 meters across, the largest single aperture radio telescope ever built, currently working through 100 candidate signals that survived 21 years of distributed computing by millions of volunteer machines. One by one, it is re-examining the signals that resisted every automated filter, the ones that the algorithms could not classify as interference or noise. As of early 2026, none of them has produced a confirmed detection. The James Webb Space Telescope is analyzing the atmospheres of exoplanets during transit events, looking for the chemical signatures of life. The deep ocean oxygen discovery complicated one biosignature. The dimethyl sulfide detection on K2-18b did not survive independent verification. No exoplanet has a confirmed atmospheric biosignature. The window is still open. The instruments are still running. The question Enrico Fermi asked at a lunch table in New Mexico in 1950 has not been answered. But the data has been accumulating, and the data says that the universe had every opportunity to fill itself with civilizations capable of being detected across interstellar distances. It had the planets, it had the chemistry, it had the time. It had 13.6 billion years and hundreds of billions of stars and 40 billion habitable worlds in this galaxy alone. And the measurement is 0. That is not an absence of information, that is information. The most important single data point in the history of human inquiry into our place in the cosmos. It says that something about the journey from the first radio transmission to a civilization that persists long enough to become visible across the galaxy is extraordinarily difficult. That civilizations like ours, civilizations that build telescopes and write equations and search the sky and ask, "Where is everybody?" are either extraordinarily rare or extraordinarily brief, or both. We are here, right now, in the window. 127 years into Garrett's 200 years, inside Duggan's demographic mathematics, watching our electromagnetic footprint shrink as our technology advances, funding the search for other civilizations at a tiny fraction of what we spend on the processes the silence suggests are most dangerous. The silence is not waiting for a better telescope. The silence is a message. It arrived 65 years ago, and we have been measuring it ever since. 0, the most informative number in the history of science. The universe is silent for a reason, and the reason is not out there among the stars. The reason is here, in what happens to intelligence when it reaches this point, in what we are building and what we are not building, in the speed at which capability outpaces wisdom, in the mathematics of reproduction in a world where reproduction is a choice made against honest accounting. The instruments are still running, the number has not changed, and somewhere in the specific quality of that unchanged number, in the 65-year convergence of billions of null results from the most careful search ever conducted for the most unmistakable evidence of intelligence in a universe that appears to have had every chance to be full of it, is everything that matters about what happens next. Not out there, here, now, in the window, while it is still open.